All right, back with part two. How the name of this function, logarithm base 2, how we write it is new to us as well. Log, and then what's called a subscript. It's kind of like the opposite of an exponent. It gives us the base of x, log base 2 of x. And notice a few things about this logarithm function. Its domain, the domain, isn't all real numbers like the exponential function. The domain is sort of only the positive numbers, right? X has got to be greater than 0. The range, though, think of all the shadow on the y-axis. Well, it looks like that's going to continue forever. Over here, the shadow is going to keep going up. In fact, it's y is any value. And if that looks familiar, that's just the switch of the exponential function, right? The domain was all real numbers, and the range was y has got to be greater than 0. So these have switched, and that makes sense because the inverse function is just when the x and y coordinates switch. All right. Exponential and logarithms, because they're inverse functions of each other, we can go back and forth between the two forms and have a look at this, okay? This is what we're used to, the exponential form of this statement, this function. Notice where the exponent is. That's the exponent. And so if someone asks you, what is a logarithm? A logarithm is the exponent. See that? X, it is the exponent. See where the base is here? I'm going to make this smaller because otherwise it'll be a mess. See that? There's the base. And then the other part, the y here, is kind of like the power. That's kind of like the answer for an exponent question is kind of the y. That's the power. And so let's get used to this. Express in log form. Well, how does this work? Well, this expression is the same as log. The base is 3. The power goes in the inside, and the exponent is on the outside. Log base 3 of y is x. And that's a function form. But these statements, this is just a exponential statement, right? 2 to the exponent 5 is 32, right? But in log form, we can make the same statement here. Okay, we can make the same statement because I could say log base 2 of 32 is equal to 5. What's the exponent? The exponent of 32 base 2. And a way to think of this that we're going to get used to soon, and let me write this sort of underneath, is we think of log as the opposite operation of the exponential function. So we could think of, if I wanted to, I could take a statement and I take the log base 2 of both sides, just like we would take the inverse sine of both sides to undo something. And so if I think of log base 2 of both sides, log base 2 of this is going to be, just what we wrote on the left side here. But on the right side, I get log base 2 of 2 to the exponent 5. So we know that the answer is just 5. So this part here kind of wipes each other out. Log base 2 and exponential function base 2 wipe each other out. That's kind of like having x squared and square root. Those are opposite, x plus 3 and minus 3. Well, they're opposites, aren't they? Well, log base 2 and exponential function base 2 are just opposites, and they wipe each other out. So file that in the back of your brain. Here we go. Next one. Again, we just want to switch styles. I think of this as log. What's the base in this one? Is 7. The power is 1 over 343. and then the exponent, the answer is minus 3. And again, if I wanted to think of it as an operation, I think of taking the log base 7 of both sides, and then I'm left with minus 3 on the right-hand side. Here, we're going the opposite way, to express an exponential form. So here, the power, the inside thing is y, the base is 4, and the exponent is x. This is more familiar for us, but again, if I want to think of it, what's the opposite operation? Well, what's the opposite operation of log base 4? It's exponential function base 4. So I could think of it as the left side going in the exponent and the right side going in the exponent. And again, I've got this idea of an exponential function and a log function wiping each other out, and then I'm just left with the inside thing. Okay? So here, base is 7, exponent is 2, and the power is 49, and 7 squared is 49. This makes sense. And now I'm starting to get used to this log business. The inside thing is 1 over 27. The base is 3. The exponent is minus 3. And does this make sense? Yeah. Negative exponent means 1 over 3 cubes, 27, 1 over 27. But again, just as we're going, you don't necessarily have to write this down. If I want to think about changing this, getting rid of the log base 3, I'm thinking about opposite operations. The opposite operation of log base 3 is exponential function base 3. Here, I got a function and its inverse function touching each other, so they wipe each other out, and then I'm left with the expression that I know is true. This is the exponential function. Cool. This idea will allow us to start solving problems, and this will feel a lot like the exponential problems that we've done before. I'm going to take 2 approaches for this one. Maybe one here and one on the margin. Can I maybe blow this up so I got more room? Yeah, good. Much better. So one way to think of this is, okay, I got no idea how to do this. Let's change it into something that's familiar. This is asking me, if I have 81, what's the exponent base 3? If I let that exponent base 3 be x, then change the form, I see the base is x, or sorry, the base is 3 and the exponent is x. Now this is a familiar question, right? And I see x is equal to 4. That's the answer. Now, a different way of doing that, I think a sort of a more efficient way is, well, let's think of, if I can write this inside thing as 3 to the exponent something, I'll have a function log base 3 and its inverse touching each other. Remember this idea, right? The square root of x squared. If I could get this, they wipe each other out. I'm left with whatever's on the inside, right? A function and its inverse wipe each other out. So if I could write this as 3 to the exponent something, these two things here will wipe each other out. And then the answer is just 4, like I did here. This is fewer steps. And this is what we want to do. We want to start thinking of logs, separate from their exponential statements, just because it's faster. So here, the base is 10. So if I could somehow figure out how to write 100 as a power of 10, 10 to the exponent something, they'll wipe each other out, and I'll be just left with the answer. Well, that one's easy. 100 is just 10 squared. These things wipe each other out, and we're left with 2. Now, a couple of notes about this question. It feels like this lesson is full of a couple of notes. I realize that it's a bit of a long lesson, but I don't think it's too difficult. Log base 10, we usually don't write the 10 because base 10 is used so often that it's called the common base. And so log base 10 is called the common log, and we usually don't write it in. So if we just don't write a base in here, it's implied to be 10. Okay? So this other one, we see this is implied to be base 10 over here, and we'll get to that one in a second. What's nice is this base 10, and this is the exciting part, it's a button on our calculator. Do I have it? Is it a button on this calculator? It certainly is. You see that? So if I wanted to find, and this is the older style calculator. Whoops, where did everything go? No problem. Hold on, I need my calculator back. This is the older style calculator where I got to put the inside thing in first and then hit log, and then it answers it too. Pretty slick, eh? New button on the calculator. Other folks that have newer calculators that are used to typing in things the way they appear, I'm going to use the graphing calculator to show you that. Back out to, this is sort of the normal calculator mode, not a graph, so second mode quits this, and now I can put in normal math stuff here. 5 times 9, I hope you don't put that into your calculator. But now, log of 100, I just go, see, there's the log button, log, and it's implied to be base 10 of 100 and fantastic 2, right? So isn't that awesome? Now we know a new button on our calculator. And so notice how good this is, because if we think of what question this solved, if I change this to exponential function, these are the sorts of things we've been solving using the graphing calculators lately. It's, 10 to the exponent x is equal to 43, and I can't write 43 as it's not 10 squared or 10 cubed or something like that. 10 to the exponent something here. Well, I don't know. And that's when we were using the intersection function, and we were using guess and check, and we were using all these things. I don't know what it is. I know it's somewhere between 1 and 2, because if this was 2, the answer would be 100, but it's not. And this I can just jam into my calculator, right? This is awesome. So I go log of 43, fantastic. It's 1.633. I didn't have to use an intersect function. It's a button on my calculator, and that makes me really happy about that. So I just say log. Of course, I've forgotten what the answer was, 1.63. And that's approximate, right? A few other things about this. Log of negative 12. Well, let's just try that. This is common base 10. Log of negative 12. Well, negative 11 would be almost the same, but let's stick to the question. Non-real answer, whatever that means, and if you use your scientific calculator, it gives you an error. So error, this is impossible. And if I think back to my graph, if I had an input of minus 12, it would be way out here. What's the answer there? Well, the domain, we can only take the log of a positive number, and that makes total sense, because if I were to change this to its exponential function, I'm looking for the exponent so that I get an output of negative 12. Well, what exponent is going to give me a negative number? Never ever am I going to get a negative number out of that, and that makes sense with our graphs, because never ever am I going to get an answer for an exponent question that's minus 12. Okay, so I can't take the log, can't take log of a negative. That's a good thing to remember. Okay. Back to normal log questions here. Notice I can't do this on my calculator yet. This button on my calculator was base 10. And base 10. On almost all of the calculators, it's base 10, right? Base 10. And so how do I do base 2? Well, luckily, I can actually figure this one out, because remember, the whole idea was to find log base. If this, I could find 2 to the exponent something that gives me 1/8, then I've got it. And notice 1/8 is equal to 2 to the exponent whatever. Well, 8 is 2 cubed. 1 over 2 cubed, it's minus 3, isn't it? Then I got log function and exponential function that are smashing into each other. They annihilate each other, and um, the answer is -3. Would be nice to be able to check this on a calculator, but can't do it. And notice this makes sense if I were to use my first technique of changing this to its uh, to its exponential um, form. Inside thing is 1/8. The base is 2. What's the exponent? We've solved this question already, haven't we, earlier? And so this makes sense. And I'm hoping that we're thinking about this more and more like this. Um, Another note, I know you're sick of notes. Uh, the homework, we're actually going to a different textbook along to supplement our normal textbook. We've got a hardcover textbook, so you'll want to grab one of those and work on that. Of course, you can take them home if you want to. We'll have a sign out list in class. But that's what the AW means, Addison Wesley, and that's the other textbook. Okay. All right, that's it for this day. Stay classy, Northwestern.